So last time we covered how to multiply matrices together, and this time we're going to be learning about an interesting property that those matrices have. We're learning about something called the determinant. So this is called the determinant. The determinant is only exists in what are known as square matrices. So what I mean by that is a matrix with the same number of rows and columns. So for example, a 1 by 1 matrix, a 2 by 2 matrix, a 3 by 3, a 4 by 4, a 10 by 10, a 20 by 20, and a 100 by 100, whatever. As long as they have the same number of rows and same number of columns, that matrix has something called the determinant. If we have a 1 by 1 matrix, let's call it matrix A here, it would look something like this, where it'd be a matrix of one number. The determinant would just be equal to that number that's inside of there. Okay, that's kind of boring. If we have a 2 by 2 matrix, however, that's where it starts to get a little more fun. If I want to find the determinant of a 2 by 2 matrix, and let's say our matrix is A, B, C, D. So we have 4 numbers in there. I'm calling them A, B, C, and D. The way we write this is we write it as DET parenthesis A. Or another way to phrase it, if you remember back to vectors, remember we have this thing called magnitude of vectors? Determinant isn't quite the same thing as magnitude, but it is related. And so what we can do is we can bring back that notation. And so sometimes what people do is, if you notice here, here's the bracket symbols they're using for the matrices. When we're trying to say that we're taking a determinant of a matrix, we just draw vertical lines. We don't put like the little end pieces here. We just draw vertical lines. And the formula for the determinant would just be A times D minus B times C. So it's just this diagonal minus this diagonal. It's A times D minus B times C. It's this diagonal minus this diagonal. Okay, let's see it at work. So let's evaluate the determinant of matrix A. So I want to find the determinant of matrix A. So that's 8, -2, 3, 3. And please notice that for my matrix here, I didn't actually write it in matrix form because I'm looking for the determinant. I just wrote it with the vertical lines. I didn't put like the little things at the end. So this is equal to A times D, so 8 times 3, minus, and now B times C, -2 times 3. 8 times 3, 8, 16, 24. Very badly written, 24. Minus -2 times 3. -2 times 3 is -6. So I have minus -6. Double negative there turns this into 24 plus 6. And I'm getting 30. Your determinant will always work out to just be a number. It is just a number. And that's sort of why they bring back this notation of magnitude. Remember when we found the magnitude of a vector? Even if it was a vector, you got a number for an answer in magnitude. When we take the determinant of a matrix, we will always just get a number. That is sort of why they're reusing this notation. They don't mean exactly the same thing, but they are very close in their meanings, which is why they reuse the symbol. Something else, an interesting idea, is let's say we had a matrix that was bigger than a 2 by 2 matrix. For example, a 3 by 3 matrix. There unfortunately isn't a super nice equation to find the determinant of a 3 by 3 matrix or higher. The equations there start getting to the point where no one will ever memorize them. It is just not worth the effort. So what people do is they came up with this idea of a minor. Basically, it's an idea that lets us look at just pieces of the matrix. And here's what I mean by this, and I'll come back to cofactors in a second. So, to find a minor, we need to pick a row or a column that we want to expand across. We need to pick one row or one column, and I don't really care which one you pick. For the purposes of this, I'm going to follow this first row, okay? I'm going to follow this first row of 1, 2, 4. But, again, I'll make this crystal clear. You could have picked the second row. You could pick the third row. Heck, you could do first column, second column, or third column. I don't care. It all works out because it is a square matrix. To find the minor, we need to do each one of these individually. So I'm going to start by finding the minor of element 1, 1. So I'm going to start here, because this is in the first row and the first column. To find the minor, if I want to find the minor of 1, 1, basically what I'm doing is I'm trying to find the minor of this number right here. To do this, we need to block out all the numbers in this row, and we need to block out all the numbers in this column. So effectively, what I'm doing is I'm sort of like, I think of it as putting a pencil, so I can't see these numbers anymore along here, and a pencil so I can't see the numbers along here anymore. And then I'm only able to see these 4 numbers left over. The minor of 1, 1 is just the determinant of that matrix. It is just the determinant of, in this case here, 3, 5, 1, 4. Minor 1, 1 gives us the determinant of that matrix. And this is now just a 2 by 2. This is now that really nice formula we had a second ago. So I'm going to do 3 times 4, which is, and once you do them enough, you can sort of skip ahead. 3 times 4 is 12, minus 1 times 5 is 5. I'm getting 12 minus 5 is, what would that be? 7. And so I'm saying minor 1, 1 equals 7. But we're not done. That was just the first element. Now I'm going to move on to the second element to find minor 1, 2, to find the minor of row 1, column 2. This time, I need to block out not row 1, column 1. I need to block out row 1. Oops. Could it block out where I want it to block out? I need to block out row 1, column 2. Okay, one more try, and then I'm going to do it a different way. Okay, let's try it this way. I need to block out row 1 and column 2. I need to block that column out. If I do that, I'm left again with a 2 by 2 matrix, but this time of -1, 5, -2, and 4. All I did was block out my first row and now my second column. Then I'm left with 4 numbers of -1, 5, -2, 4. This is something that I can evaluate quickly. So I'm going to take the determinant of this now. -1 times 4 is -4, minus -2 times 5 is -10. Watch out for my double negatives there. I end up with +6 as an answer here. And that would be minor 1, 2. Lastly, I need to keep going because I have one more element to go. So I'm going to go minor 1, 3. I'm going to go minor 1, 3. And so this time, I'm not going to block out column 2. I'm going to block out column 3. I'm going to block those 2 numbers out. And so now, the only numbers I have left are -1, 3, -2, 1. So I'm going to take the determinant of the matrix -1, 3, -2, 1. So that would equal -1 times 1 is -1, minus -2 times 3 is -6. Watching out for the double negative, I think I'm getting +5. Those would be the 3 minors if I went along the first row. The numbers that you get might be slightly different if you go along a different row or a different column. But we also have something that I kind of skipped over. We have an idea of something called the cofactor. Okay, I know that's a scary looking equation right here. This equation right here looks scary. It is not as bad as it looks. So, for example, that's minor 1, 1. I skipped over this on purpose. If I want to find cofactor 1, 1, all I need to do is it's -1 to the power of I plus j, the row number plus the column number. In this case, 1 plus 1 is 2, times the minor ij, which we just got was 7. Well, -1 squared is 1 times 7 is 7. So that means my cofactor for this row would just be 7. I mean, cofactor for this element would just be 7. If I want to find cofactor of minor 1, 2, so cofactor 1, 2, that would just equal negative 1 to the power of 1 plus 2. 1 plus 2 is 3, times the number we got here a second ago, which is 6. Negative 1 cubed is negative 1 times 6 is negative 6. Last but not least, if I want to find cofactor 1, 3, I'm just going to have negative 1 to the power of 1 plus 3, which is 4. And times 5, negative 1 to the fourth power is 1 times 5 is 5. You might have noticed it as I was writing it, but there's a really cool pattern with this. No one ever writes out the formula this way for this thing. It's too much work. The answers we got were either identical to the minors, like we got in the first one and the last one, or it's the opposite. And the way I know which one it is if these numbers here, if the row plus column is an even number, so 1 plus 1 is 2 or 1 plus 3 is 4, the cofactor will just be the exact same as the minor. It'll be just the exact same thing. If the row plus column is an even number, so in this case, if I did row 1, column 1, 1 plus 1 is 2. The cofactor is just the exact same thing as the minor. Whereas here, when I did cofactor of 1, 2, 1 plus 2 is 3, I will get the opposite. So what that means is if it's even, if this adds up to an even number, it's just the same as the minor. If it adds up to an odd number, it's just the opposite of the minor. So, a good question is, why are we doing this? Why does this matter? Because to find the determinant of a square matrix, we have to multiply each element of the first row by its cofactor. We need to multiply each element of the first row by its cofactor. So here's what I mean. I'm going to go along this first row here, and I need to find their cofactors. So to find the determinant of this matrix, we first things first need to find the cofactor of, in this case, 1, 1. I need the cofactor of 1, 2, and I need the cofactor of 1, 3. I need to find those three cofactors, and then I need to multiply them by the elements in each spot. So to not make this harder than it has to be, to find cofactor 1, 1, the first thing we need to do is find minor 1, 1. We can't find cofactor 1, 1 without finding minor 1, 1. So what I'm going to do is I'm going to block out the entire first row, and I'm going to block out the entire first column. I'm left with just 2, 3, 4, negative 1. If I multiply this out, 2 times negative 1 is negative 2, minus 4 times 3 is 12. I'm getting negative 14. So minor 1, 1 is equal to negative 14. So that means cofactor 1, 1 is also equal to negative 14. The reason is because 1 plus 1 is 2, which is even, so they're the same. I also need now minor 1, 2. So I'm going to still block out the first row, but now I'm going to block out the second column. So I have, what would I have? 5, 3, 6, negative 1. So I have 5, 3, 6, and negative 1. And we are going to expand this. 5 times negative 1 is negative 5. Minus 6 times 3 is 18. And then what would that be? Negative 5 minus 18, that would be negative 23. So that would be minor 1, 2. But that is not what cofactor 1, 2 is. Cofactor 1, 2 would actually just be equal to positive 23. Cofactor 1, 2 is just positive 23 because 1 plus 2 is 3, which means it's odd, which means it's the opposite of minor 1, 2. And almost there, I need minor 1, 3, which is equal to, and I'm going to again block out now the first row and the third column, and I'm left with 5, 2, 6, 4, 5, 2, 6, 4, expand along our determinant. 5 times 4 is 20. Minus 6 times 2 is 12. 20 minus 12 is 8. And so cofactor 1, 3 would just be equal to 8. Here's our three cofactors. We have negative 14, 23, and 8. We're almost done. To get the determinant, here's what I need to do. I need to multiply each of these cofactors. This is cofactor 1, 1, cofactor 1, 2, cofactor 1, 3 by the element that was in that spot. So for example, cofactor 1, 1 is negative 14. So I'm going to do negative 14. If I can get the mouse to work. I'm going to do negative 14 times, and now I need to multiply this by the element that was in that spot 1, 1. In this case, that would be negative 2. So it would just be negative 2 times negative 14. And now I'm going to add it to the next one. I like to think of it more as the element times the cofactor. So if I'm going to use the next one of cofactor 1, 2, I need to get the element in 1, 2. This is going to be 0 times 23 plus, and now I get the third element, which is 2 times my cofactor of 8. And now it's just arithmetic. Negative 2 times 14 is 28. 0 times 23 is 0, plus 2 times 8 is 16. Add them together, what would that be? That would be, what? That would be 40 something. 48 plus 6, that would be 44. The determinant of this 3 by 3 matrix is 44. Okay, I can hear you now. That was a lot of work. Mister, we are not doing that every time. That is too much work. I agree with you. It'd be really nice if we had a formula, but we're not really going to get a nice formula for this. So instead, mathematicians got bored, and they came up with an alternate way to do this. So if we imagine the exact same matrix we had before, this matrix here, I copied it down, and I'm going to do something kind of weird. I'm going to take this first column and second column, and I'm going to copy them over next to it. So it almost becomes a bigger matrix. I'm not saying it's another matrix, but I'm just copying the numbers down. So I have negative 2, 5, 6, and I have 0, 2, 4. To find an alternate method for a 3 by 3, what we do, and this is going to sound weird when I say it this way, we're going to add the products of the 3 downward diagonals and subtract the products of 3 upward diagonals. And here's what I mean by this. I'm going to multiply this diagonal right here together. I'm going to add it to this diagonal multiplied together right there. And I'm going to add it to this diagonal multiplied together right here. And I'm going to write this part out. So it's going to be negative 2 times 2 times negative 1 plus 0 times 3 times 6 plus 2 times 5 times 4. That's us adding all the downward diagonals. Then we are now going to subtract all the downwards diagonals. So I'm going to erase these circles here, and hopefully you can see what I was, oops, didn't mean to erase that number. It was a 2. We are now going to erase all the we're going to subtract all the upwards diagonals. So I'm going to, for example, have 6. I'm going to have 4, 3, and negative 2. And I'm going to have negative 1, 5, and 0. So I have 6 times 2 times 2. I get the pen to write. 6 times 2 times 2 plus 4 times 3 times negative 2 plus negative 1 times 5 times 0. And now we're going to do this arithmetic. So negative 2 times negative 1, that's a 4. Plus, I'm a little lazy, 0 times all this garbage is just 0. Plus 2 times 5 is 10, times 2 times 5 is 10, times 4 is 40. Minus, and now we're going to do this parenthesis, 6 times 2 is 12, times 2 is 24. 4 times 3 times negative 2 is negative 24. And this last one here has a 0 in it, so that just works out to 0. Positive 24, negative 24 just go away, so everything in this term goes away. 40 plus 4 is 44. So we got the exact same answer as before. So this is how to take the determinant for a 2x2 matrix, a 3x3 matrix, and so on. By the way, this pattern actually does work for further size matrices. You just have more and longer diagonals, is all it is. So I hope this made sense. Please let me know if you have any questions.